Okay, so this is the second example from week 8, and I would look to look at a situation where we're going to be dealing with a force, and we're going to be showing that it's non-conservative, alright? And so this is problem 4 from 2012 exam 2, and so I'll show you that briefly, and I'll make sure to put the link in the description for the problem. So it's a long problem. I don't want to go through reading it, so please, on your own time, just go through, read it, and see what it's all about before you watch this video. Because otherwise, this video is going to be very confusing. Okay. All right. So, as described, we have a well, something like a crate or something or another being moved around in a river. So we have two river banks. Okay, we have one on this side and one on this side. And what we're going to do is we're going to consider two different paths. So path 1 is the path that goes from AB to CD, but first goes to point AD and then to point CD directly. And then we're going to also look at path 2, which goes from AB to CB and then from CB to CD. Okay, and we're going to look at the work done by the applied force. So we are told that whenever the box or crate or whatever it is traveling horizontally, okay, it has a the applied force is going to be constant, Fh, and that's the force needed to be applied, so the velocity of the crate remains constant, okay? And when we're traveling along vertical paths, so in the y direction, we're looking at a force that depends on the x location. So it's equal to F0, a constant, times the x-coordinate along this vertical path. And that too is the force required for the velocity to remain the same. So let's look at part A, where we look at the work done along path 1. So once again, that is the path which goes from AB to AD, and then from AD to CD. So it looks like I left something off down here. So let's get this fixed. We're going from AB, we're going to use the definition of work. So that's the integral from our starting point, AB, to our ending point, CD, of the force applied dr. Okay? And this is an integral over path 1, as indicated by that 1 in the circle. Okay? And so this is equal to, well, let's look at the path. So path 1 first goes along this vertical part, from AB to AD. Alright? And so the applied force there is going to be F0 times the x-coordinate there, and the x-coordinate is A. So we're going to have an applied force of F0A from AB to AD. And so that's what this integral represents. And then the next part of the path, we add then the work done along the horizontal part. And from AD to CD, we have a horizontal force, which we're told is constant, and that's FH. So it's FH from AD to CD. Okay? And now, the x-coordinate, let's once again just remind ourselves, although the force is F0x in the vertical direction, on path 1, the x-coordinate is going to be A, as we're going to have this vertical force applied. So this what I mean by vertical is along the y direction. Okay? And so we're going to have a total force of F0 times the x-coordinate A. So we have F0A there. Okay. So performing these integrals, these are two constants multiplied by each other. So the indefinite integral is F0AY. And the final y-coordinate is D. Okay, and the initial y-coordinate is B. So we get F0AD minus B. This is also a constant, so the indefinite integral is FHX. And we're integrating over x here, so we look at the final x-coordinate C and the initial x-coordinate A. So it's FH times C minus A. And the sum of the work done along each leg of the path is the total work done along path 1 by the applied force. Now how about path 2? So what's path 2? Well, path 2 is this pink path, which goes from AB to CB, and then from CB to CD. Okay? And so, from AB to CB, we have a horizontal force of FH. And from CB to CD, we have a vertical force of F0 times the x-coordinate there, where the x-coordinate is going to be c. So we have a vertical force of F0c. So there we go. Our vertical force F0c and our horizontal force FH. From AB to CB and then from CB to CD. Okay? So let's check that. AB to CB, CB to CD. Okay? So once again, these are both constants, and we are going to get this. So verify that you get this as well for the work applied along path. Sorry, for the work done by the applied force along path 2. And part C asks, what are the components of the force of the water on this crate or barge, whatever it is? So if we consider when it's moving horizontally, our free body diagram looks like this. It's going to be FH to the right, so some applied force to the right, FH, and then to the left it's going to be F0, FW, was what we're going to call the x component of the water. Okay, let's just have W here. And then down here I've called it FWX to show that it's in the x direction, as it doesn't matter what you call it. But let's note that we're moving at a constant velocity. So the net force has to be 0. So the sum of FH and the x component of FW is 0. So why did I put it as a positive value and a negative value here? Well, by putting it in as a positive value, that means that the answer will be positive or negative, and the sign of the answer will tell us which way it's moving. So if I put it in as positive, I get Fwx equals negative h, which means the force of the water is to the left with a magnitude of Fh, as we might expect. Okay, and so now we have the case where we're moving vertically. And remember, the vertical force is F0 times the x-coordinate along the path. And so if we sum the forces, which is going to be the force of the water and the applied force, we'll find that the applied force in the y direction is going to be negative F0x, so F0x pointing down, once again, because the acceleration must be 0 in this case. And so we're asked, is this force of the water conservative? And one of the criteria that's easiest to use to prove whether or not this is conservative, is that the work done by a conservative force, so if we were considering the work done by the water from AB to CD, okay, then it would have to be the same no matter which path we take, okay, whether we take this path or we take this path. Now, as we've shown here, right, as we've shown down here, the components of the water's force are just going to be negative the components of the applied forces. And so the work done along path 1 by the water, instead of the applied force, will just have a minus sign in front of all this. And the work done by the water, okay, we'll just have a minus sign in front of this as well, along path 2. So the work done by the water along path 1 and path 2, we can compare them, and they must be the same if it's a conservative force. Okay, so is it the same? Well, let's look. So here we have F0A times D minus B and FHC minus A, and down here we have FHC minus A, but we have F0C D minus B. So remembering that all it changes is an overall minus sign, it doesn't matter, although these terms would be the same, these two terms would not. So the work done by the water around path 1 and path 2 are both 0, so it's not conservative. So this is like, also another way to think about it is like friction, right? This is definitely going to be a velocity-dependent force. For if we looked at a path which went from AB to CD directly, so it cut down the diagonal of this sort of overall rectangular path. Okay, if it cut down the diagonal, then we'd have a water force which points this way, and the x components Although it will be FH the entire time, the Y components will change as X changes, right? And so there is no potential function given by what we found earlier that will cover for that. And lastly, the last criterion for conservative force that it also violates is that the force done by the water around a closed path must be zero. Well, the force done by the water from here to here is going to be negative, from here to here is going to be negative, here to here is going to be negative, and here to here is going to be negative. So if we take this path around this way, all we get is negative work done by the water because the water's force will always oppose the direction of motion, so there's no way we can get zero work done around a closed path. So there's a few different ways you can show that this is not a conservative force. Okay, and once again, if you're watching this before the exam, I wish you the best of luck on the exam. Okay, bye.